This is the Redeem Myself Motors and Generators video. So we're going to start off where the board finished off today. We have our motor coil sitting inside the magnetic field, which you can see here. We have what we wrote in class today with the force and the torque. To correct it for your notes actually make sense and actually work, you need to add an N in here. I forgot to say this is N coils. You'll get N BIL sine theta for the force, and therefore the torque will be N BIL d sine theta, etc. The total torque will be 2N BIL d sine theta, which is 2N BIL d, which is N BIA. I forgot to stick the cos theta bit in, but all you need to write there is, but as the coil rotates, the force perpendicular to the coil decreases, proportional to cos theta, and therefore the torque is equal to N BIA cos theta. And that's all you've got to add to your notes, but let's look at what's really going on. So what I've done is drawn that same motor coil. If we just go back a second, we can see right now this motor coil is sitting, I suppose you can say, parallel to the magnetic field. So the magnetic field is going on these lines here. The coil is parallel to them. If you use your left-hand rule, you'll see the force on side AB is down, the force on CD is up, and that means that coil is going to start rotating. So what I've drawn here is that coil starting to rotate, and what it's done is rotated by an angle of theta degrees. And that theta is in orange because that theta in orange is the angle between the coil and the field. But if we look at the individual sides, the individual wires of the coil, we can see, we know it's side A and B and side C and D that are actually going to have a force on them because they're the ones that are perpendicular to the field, whereas side B, C and AD are parallel to the field. The angle between those wires, AB and CD, and the field is this red angle here, which I'm going to call theta. And as we know, if this coil starts to rotate, and if we think about it down here on this diagram drawn from the end, which is this N diagram down here, right now the current is going out of corner D and into corner A. As this coil rotates around, and I've drawn some dotted lines to represent the past and the possible future, wherever this coil happens to rotate, these wires, CD and AB, are always going to be at 90 degrees to the field. So that red angle will always be 90 degrees. No matter where you draw this, you're always going to have your field lines, magnetic field lines going across to the right, and the current either going into the page or out of the page, so into the page or out of the page. And that means this red angle, this angle between the wire and the field, in a motor, that angle is constant, and it's constantly at 90 degrees. And therefore the wires stay perpendicular to the field, and we're going to have force formula here, F equals BIL sine red theta, the angle between the wire and the field, or for a motor, F equals N BIL sine theta, because we've got more than one coil. That means that sine theta, that red sine theta, stays equal to 90, which means sine theta equals to 1, or F equals N BIL. So the force on those two wires is constant. And we can draw that there. Let's call this force on wire CD. It can be going straight up. We can call that force, if I can get the colour right, we'll call that's the force on wire CD. And this down here is the force on wire AB, and they're going to be in a constant direction, and that force is constant. So if we call down negative and up positive, that means the force on wire AB will always be constant at a negative value of negative N BIL, and the force on wire CD will always be a positive value. This is force CD, and it's always going to be equal to positive N BIL. No matter where that coil turns, those two forces will stay constant on those sides of the wire. But we know that torque is a little bit different to force. And torque is the product of the force times the distance. But this isn't the total force. This is the component of the force that's perpendicular to the coil. And that force, the component of force perpendicular to the coil, changes as theta changes, as that orange theta, the angle between the coil and the field, changes. And that's what I've drawn down here. I don't expect you to derive this, but basically here is that force, this purple force I drew previously, F equals N BIL sine F equals NBIL, or force on CD, is N times B times I times L. But this is the component here that's perpendicular to the actual coil itself. And we can derive that to be force, which is causing a torque on side CD, equals NBIL cos theta. And you can do the maths here. That angle there's theta, and that angle there's 90 degrees. That means that angle there must be theta as well. So the force that's actually causing the torque in this particular situation on side CD is F equals NBIL cos orange theta. And by a similar argument, the force down here, which is perpendicular to the coil, which is causing the torque on side AB, is NBIL cos orange theta. So now we can calculate the total torque on the coil. The total torque on the coil is going to be the torque on side AB plus the torque on side CD. They're both acting in the same direction. And we can now write that as, well, the torque on AB based on this formula here, will just be the force causing a torque on side AB times the distance, plus the force causing a torque on side CD times the distance, which now we can get from down here, and we can get from over here, and then we can write this force causing a torque on side AB is just NBIL cos theta, and that's all times that distance d from the pivot, plus, now we can get it from over here, the purple one, we can get it's equal to NBIL cos that orange theta again, the angle between the coil and the plane, all times d, which is the distance between the center line axis and that force. And obviously all of those terms are just exactly the same. So that whole thing now can just simplify to be 2dNBIL cos orange theta. But if we now go back and look at our diagram of our motor, we can see the distance of half that length is d, so this whole length would be 2d. The side length here is L, so if we take those terms out from over here, we can say, we'll call that 2dL outside of NBI cos theta. And knowing that 2 times the distance times the length in this case is just the area of the coil, we can now derive that that's equal to N times B times I times A times by cos theta. And at last we've managed to derive that thing. We didn't need to derive anyway, but hopefully along the way you've learnt a few things. Torque has made a bit more sense, the angles have made a bit more sense, and the concept that the force on each long length stays constant. It's actually a very important concept. It's important you understand the actual force on each length stays constant, even though the torque changes, and even though the component of the force that's causing the torque does change. But those actual total forces stay constant on those wires. Phew!